Have you ever considered how satellites are in space? How do they move, maneuver, or communicate with Earth? Or even, how do they adjust their trajectories to meet the objectives of their missions? Did you know that the same set of physical laws that govern the trajectory of a planet around a star are also the same laws that apply to a satellite as small as the Pocket Cube in orbit around the Earth? That's right. Astrodynamics is the science that studies the movement of celestial bodies, including satellites and other artificial objects, under the influence of gravity and other forces. It is essential for designing and operating satellites, from large constellations to our compact pocket cube. And to understand how the movement of these small satellites works, we need to delve into a universe of laws, equations, and calculations. But don't be scared. This universe is as fascinating as it is essential for understanding and controlling what happens in space. At a time when space exploration is no longer something distant or restricted to large space agencies, such as NASA or ESA, understanding the principles that govern the movement of celestial bodies has become essential for space missions of all kinds. Pocket cubes are incredible precisely because they are small units with immense potential to collect data and carry out scientific, technological, and communication missions. Despite their limited size and capabilities, the laws of physics that govern their movements are the same as those that command large spacecrafts, such as the giant Jupiter 3 satellite, launched in 2023 by SpaceX, or even the Parker probe, launched by NASA. To understand how pocket cubes can be launched, positioned, and controlled, we must start with the fundamentals of astrodynamics, with an emphasis on orbits, orbital maneuvers, and the unique challenges imposed by the miniaturization of these satellites. No matter which satellite you have in mind, the first thing you must understand is that space is not empty and lawless. The movement of bodies in space is governed by gravity, inertia, and a set of equations that have been formulated over centuries, based on the studies of great scientists such as Isaac Newton and Johannes Kepler. Newton's laws and the law of universal gravitation are the starting point for understanding how bodies move in space. According to Newton, bodies remain in their state of motion or rest unless an external force acts on them, the famous first law or law of inertia. In the case of pocket cubes, this force comes from Earth's gravitational field, which keeps them in orbit. In reality, we think that entering orbit is an infinity fall, but then we would have to think about Einstein's general relativity. The law of universal gravitation tells us that the attraction between two bodies depends on their masses and the distance between them. A satellite orbits the Earth because it is in a kind of infinite fall. It moves forward at a certain speed, while Earth's gravity continues to pull it downwards. But since the Earth is round, instead of falling on the ground, it continues spinning around the planet, always falling but never reaching the ground. Kepler's work further refined this understanding by detailing the motion of planets around the Sun, and these discoveries apply directly to the motions of satellites. Kepler formulated three fundamental laws that accurately describe the orbital motion of celestial bodies. Among them is the idea that planets move in elliptical, not circular, orbits. But what does this mean for pocket cubes? Depending on the mission and planet trajectory, a pocket cube's orbit can be not only circular, but also elliptical, parabolic, or hyperbolic. Each of these orbits has different practical implications for the satellite, for its ability to communicate to its lifetime in space. You've probably heard of elliptical, circular, and other types of orbits. But how do these apply to PocketQubes? The important thing to understand is that satellite orbits are not just random trajectories, but are described by its specific orbital parameters. These parameters determine the shape, altitude, and position of the satellite along its orbit. If you have a PocketQube, how do you know what its orbit will be? How do you make it perform maneuvers and adjust its position in space? To do this, we need to explore a fundamental concept of astrodynamics: Kepler's orbital elements, or simply orbital parameters. These parameters are crucial to defining the trajectory of a satellite and include the semi-major axis, which is the distance from the center of the ellipse to the furthest point of its perimeter; the eccentricity, which defines how elongated the orbit is, whether it is more circular or more elliptical; and the orbital inclination, which describes the inclination of the orbit in relation to the reference plane, such as the plane of the Earth's equator. We also have the argument of the periapsis, a strange name, but it is simply the point in an orbit where a satellite or spacecraft is closest to the celestial body it orbits. And finally, the true anomaly, which is the angle that indicates the real position of a planet in its elliptical orbit in relation to the closest point to the Sun, the so-called perihelion. Think of it this way: if the planet were a race car, the true anomaly would be the little sign telling you exactly where it is on the track at that moment. A lot, right? But with these parameters, we can predict and control the position of a satellite over time. In the case of PocketQubes, these parameters not only describe its orbit, but also impact its useful life. PocketQubes, despite their small size and their limitations of energy and resources, are of great value due to their ability to be in low Earth orbit or low altitude orbits, which range from 160 to 2,000 kilometers above Earth's surface. These orbits are advantageous because they allow greater proximity to the planet, facilitating communication and satellite tracking. In addition, LEO provides good visibility for sensors and faster response times for communications. This makes PocketQubes ideal for environmental monitoring missions, Earth observation, and even scientific applications. However, one of the biggest challenges for PocketQubes is their lifespan. The reason for this is the atmospheric drag, which is caused by the interaction of the satellite with particles in the Earth's atmosphere, even at an altitude of 600 kilometers. As a result, a PocketQube can lose speed and then altitude, entering a downward trajectory until it re-enters the atmosphere and disintegrates. Therefore, the greater the eccentricity of its orbit, or the lower the altitude, the greater the impact of this phenomenon. By the way, the impact of drag varies over time due to changes in atmospheric density, which can be influenced by solar activity. This means that engineers need to constantly monitor orbital data and recalculate predictions to adjust mission plans. Speaking of mission plan adjustments, we now come to an important concept: orbital maneuvers. But before we get into this subject, we need to understand how important the choice of orbit is for the success of the mission. The selection of the ideal orbit depends directly on the mission objectives. For scientific missions, such as monitoring atmospheric phenomena or mapping terrestrial vegetation, sun-synchronous orbits are a common choice. Sun-synchronous orbits are those in which the planet rotation around its axis and the satellite translations take the same amount of time. This means that if you're on the planet looking at the satellite, it would always be at the same point in the sky or would pass over the same place at regular intervals. For communication missions such as data relay, equatorial orbits may be more suitable, depending on the desired coverage areas. In this orbit, the satellite moves parallel to the equator, without inclination in relation to it. If it is geostationary, it remains stationary in the sky for those looking at it from the Earth. If it's lower, it can make several orbits per day. On the other hand, for PocketQubes intended to observe specific high-latitude regions, polar orbits are the best option, as they allow it to fly over both poles in each orbit. But choosing the orbit is only the beginning, even if the right orbit adjustments are necessary. Therefore, we need to use maneuvers and movements to make the necessary corrections. When we talk about orbital maneuvers, we are referring to actions that alter the trajectory of a satellite by adjusting its speed. This is done by applying a force that results in a change in speed and consequently an adjustment of the satellite's orbit or even its complete transfer of orbit. However, performing a delta V change is not as simple as it seems. It requires precise planning, since any adjustment in space consumes fuel or energy, resources that are extremely limited in PocketQubes. Therefore, it is important to use the most efficient maneuvers possible. As we had seen in the case of PocketQubes, orbital maneuvers are extremely important since they may be necessary to correct the orbit after launch, adjust the inclination, or even avoid collisions with other satellites or space debris. Ultimately, orbital maneuvers are what allow satellites, whether large or small, to carry out complex and ambitious missions. One of the most efficient maneuvers is the Hohmann transfer, which allows the satellite to change orbit in a fuel efficient way, taking advantage of the laws of physics to spend as little fuel as possible. This maneuver is ideal for moving a satellite between two circular orbits at different altitudes. It works like this. First, the satellite performs a thruster burn to enter an elliptical transfer orbit. When it reaches the furthest point of this ellipse, called apoastro, it performs a second burn to contour its new orbit. But what if the difference between the orbits is very large? In this case, it may be more efficient to use another maneuver, the bielliptical transfer. This technique involves an additional maneuver in which the satellite enters an intermediate transfer orbit before adjusting again to its final orbit. Although this approach is more time-consuming, it can save delta V in specific situations, especially when the orbital differences are extreme. Now, if the goal is to change the orbital inclination, the situation becomes more complicated. The inclination is the angle between the satellite's orbit and the Earth's equatorial plane. And changing this angle costs a lot of energy. In practice, this means that changes in inclination are only made when absolutely necessary, as in the case of satellites that need to fly over specific regions of the Earth. One way to reduce this cost is to launch the satellite already at the correct inclination, choosing a rocket and a launch site that favors the desired inclination. But what about PocketQubes? How can these satellites, which have limited resources and a low-capacity propulsion system, perform efficient maneuvers? The answer lies in precise mission planning. The use of electric propulsion and fine-tuning based on the navigation tools available on board, such as solar sensors and gyroscopes. Let's take a closer look at some of these technological advances that allows us to fully exploit the capabilities of a PocketQube. One such advance that is making it easier to perform orbital maneuvers is electric propulsion. Instead of relying on traditional chemical thrusters, electric propulsion systems use electric fields to accelerate particles and generate thrust. That is, give the satellite a little push. Although these systems offer much lower displacement forces, they are extremely energy efficient, allowing satellites to perform adjustments over weeks or months. For PocketQubes, this technology is revolutionary. Due to their limited size, electric propulsion systems, such as ion engines or Hall effect thrusters, are not required. This effect forces electrons to move in a particular path, creating a plasma current that pushes the satellite in the opposite direction. This technology allows PocketQubes to perform precise maneuvers, such as orbit adjustments, without needing large amounts of fuel, something essential to increase their autonomy and prolong their mission in space. This is especially useful for long-duration missions, where small, frequent orbital adjustments can make all the difference. It is important to note that in many cases, PocketQubes rely on passive strategies for orbital adjustments. Due to the lack of active propulsion systems, passive mechanisms are inefficient and cost-effective solution. Idle breakers, for example, are panels that open to increase the contact area and consequently increase drag, which can be used to reduce the satellite's speed in a controlled manner, adjusting its orbit without the need to active thrusters. Solar sails are also an interesting option for PocketQubes that operate at higher altitudes, taking advantage of the pressure of solar radiation to perform small orbital corrections. To ensure that these maneuvers are performed accurately, PocketQubes need sophisticated navigation systems that combine high-precision sensors such as magnetometers, which we use to measure the magnetic field, gyroscopes, and even star cameras to determine the satellite's altitude and position in space. The precision of these systems is essential, as the slightest variation can result in large deviations in the satellite's trajectory. In addition to perform automatic orbit adjustments and corrections during the mission, PocketQubes benefit from the use of advanced algorithms, such as the Kalman filters, a mathematical algorithm that allows the satellite's position and velocity to be estimated and corrected in real time. We also have a wide range of sensors to ensure the correct operation of the satellites, such as attitude sensors, which are essential for controlling the orientation of PocketQubes. One of the most common sensors used to determine attitude are gyroscopes, which measure the rotation of the satellite along its three main axes. Gyroscopes are essential for stabilizing the satellite's orientation and ensuring that it is pointing correctly in relation to the Sun, the Earth, or other reference points. In PocketQubes, gyroscopes need to be extremely compact and efficient, since available space and weight are limited. In addition to gyroscopes, magnetometers are crucial sensors for determining altitude. They measure the Earth's magnetic field and can be used to help PocketQubes accurately orientate itself relative to magnetic north. These sensors are especially useful in low orbits, where the geomagnetic field is strong enough to provide accurate information about direction. While magnetometers are essential, they also face limitations, such as interference from other electronic components on the satellite and the need to calibrate the sensor over time. Another important sensor for PocketQubes navigation is the solar sensor, which helps determine the satellite's relative position in relation to the Sun. This allows PocketQubes to adjust its orientation to maximize sunlight capture, ensuring that its solar panels are always aligned to charge the satellite's batteries. In missions where orientation needs to be maintained for long periods, sun sensors become essential to maintain energy efficiency. and ensure that the satellite remains operational. Their use helps determine PocketQubes' positions, since the orientation in relation to the Sun can be used to calculate the position and adjust the trajectory more accurately. Star cameras work in a similar way, but they use other stars as references by comparing their position with a reference catalog. This navigation technique is often used in long duration missions. However, it requires good visibility of the stars, which can be affected by conditions such as the presence of clouds or direct sunlight, which can be avoided by using special lenses. In addition to attitude sensors, PocketQubes can also rely on GPS systems to determine their exact position in orbit. GPS works by transmitting signals from orbiting satellites to the PocketQube, which calculates its location based on the time difference between receiving the signals. GPS is widely used on larger satellites, but its applications in PocketQubes presents challenges. For example, there is limited space for the antenna and the need to ensure that the GPS signal is sufficiently strong, especially in low orbits. All of this data provided by the sensors is then processed and integrated into the onboard control systems. This allows for autonomous orbital maneuvers, ensuring that PocketQube can efficiently accomplish its mission, even when faced with space and resource constraints. As technologies advance and systems become more and more miniaturized, PocketQubes are becoming an increasingly attractive platform for a diverse range of missions. As the possibilities of using these satellites expand, new challenges arise. How to manage a constellation of PocketQubes efficiently? Instead of operation individually, several PocketQubes can be launched together to form a cooperative satellite network. This approach allows for tasks that would be impossible for a single satellite, such as simultaneous monitoring of multiple regions of the planet, or scientific experiments that require measurements from different spatial points at the same time. However, operating a constellation of PocketQubes presents its own challenges. Precise planning is required to avoid interference between the satellites in the constellation and to ensure that each one remains at its designed position. This may require periodic adjustments to the position of each PocketQube, either through small thrusters or passive techniques. If one PocketQube fails, the other can take over its role, making sure the mission continues. To make all these strategies viable, the use of simulation softwares becomes essential. Tools such as STK or GMAT, allowing modeling of orbital scenarios and predictions of the behavior of a PocketQube under different conditions. STK, for example, is widely used in the industry to simulate complete space missions, from launch to orbital operation. It offers powerful visualization capabilities that help understand how different parameters affect the trajectory of the PocketQube. GMAT is a free and open source tool that is ideal for those who want to perform complex calculations and custom simulations. Programming libraries such as Polyastro in Python offers a more flexible and customizable approach for engineers and researchers. These tools not only help with initial planning, but also enable the ongoing operation of PocketQubes. They can monitor changes in orbital conditions and adjust plans as needed. As orbital space becomes more congested, it is essential to take a responsible approach to operating PocketQubes. But how can collisions be avoided in a space already saturated with debris? One of the biggest challenges in operating PocketQubes is collision avoidance. The space around Earth is increasingly congested with active satellites, space debris, and new constellations of satellites being launched constantly. Because PocketQubes are extremely small, they are particularly difficult to track, making managing their trajectory a real challenge. To minimize the risk of collisions, detailed planning before launch is essential. Preliminary orbital density analysis allows PocketQube to be positioned in a less congested region of space. After launch, it must be continuously monitored to avoid dangerous approaches to other space objects. This can be done with the help of ground-based monitoring networks, which uses radars and optical telescopes to track objects in orbit. While PocketQubes are opening up new frontiers for space exploration, they also present a number of challenges that need to be overcome with planning and creativity. The first big challenge: power. Unlike traditional satellites, which can carry huge solar panels and robust batteries, PocketQubes have to work magic with a tiny amount of power. The limited size of solar panels means they capture little sunlight and generate less electricity. This forces engineers to design these satellites to operate with as little power as possible, prioritizing essential systems and turning off anything that is not needed at all times, and positioning the satellite in the right way to maximize solar energy capture becomes critical. And if power is already a problem, imagine propulsion. Most PocketQubes simply do not have the space to carry an efficient propulsion system. This means that once launched, they are practically at the mercy of the laws of physics, as we saw at the beginning of this lesson. On some missions, alternative techniques are used to perform small maneuvers. Therefore, the choice of the initial orbit needs to be very well calculated because there is not much chance for correction after launch. Now, even if the satellite is in the perfect orbit, it still faces an invisible enemy: orbital disturbances. Earth's atmosphere, even at high altitudes, still exerts some resistance on PocketQubes, reducing their speed and consequently causing their orbit to gradually decay. And since they do not have thrusters to correct this, they end up re-entering the atmosphere earlier than larger satellites. Not to mention the pressure of solar radiations that can slowly alter their trajectory and orientation, being a problem for missions that depend on precision. But the challenge does not end there. How do you monitor something so small in space? PocketQubes are difficult to track because they reflect little light and are practically invisible to many conventional radars. To know exactly where the satellite is in its orbit, engineers use tracking networks. These antennas pick up signals sent by satellites, and based on the time it takes for the signal to reach different locations, engineers can calculate its position accurately. This process is called triangulation and allows the satellite's trajectories to be monitored in real time. To maintain contact with these small satellites and ensure that missions continue to operate as planned, it is essential to have ground stations well distributed around the globe. These are issues that require not only advances in astrodynamics, but also innovations in orbital space management, satellite tracking, and the coordination of orbital maneuvers. The future of PocketQubes depends in large part on the ability to adapt the laws of physics to these new challenges, enabling these small satellites to perform increasingly complex and crucial functions for the advancement of science and technology. But regardless the challenge, one thing is certain: the future of space exploration is constantly evolving, and PocketQubes are just the beginning of a new chapter. PocketQubes face daunting challenges for their size: low power, limited space, lack of active propulsion, and all the disruption in the space environment. But the good news is, with smart planning and innovative technologies, these obstacles can be overcome. Every advance in sensors, navigation, and orbital control brings these small satellites closer to ever more ambitious missions. They are becoming more efficient and autonomous, paving the way for ever greater contributions to space exploration. And the most incredible thing is that these mini satellites prove that even with the limitations, it is possible to do incredible things in space.